Welcome to the lesson on trigonometric ratios. At the end of this lesson, you will be able to state the trigonometric ratios of an acute angle in a right-angled triangle. You will also be able to calculate the trigonometric ratios of an acute angle using Pythagoras theorem. Here's Jack. He has been given a unique problem in his math activity class. He has to find the height of the clock tower in the campus of his school. Tough job. Actually, there is a branch of mathematics called trigonometry, which can be applied to solve Jack's problem. The word trigonometry is derived from ancient Greek words, which mean study of triangles. Trigonometry is the study of how the sides and angles of a triangle are related to each other. In this lesson, we will study the ratios of the sides of a right triangle with respect to its acute angles. Let's begin by reviewing some key terms related to right-angled triangles. You may already know some of these. Triangle ABC is a right-angled triangle. A right-angled triangle is also called a right triangle. In this triangle, angle ABC is a right angle, as it measures 90 degrees. Angle BAC and angle ACB are acute angles, as they measure less than 90 degrees. Please note that angles can also be named by the vertex when they are formed. For example, angle BAC can be referred to as angle A, angle CBA as angle B, and angle ACB as angle C. The longest side of the triangle is side AC, which is opposite to the right angle. This side is called the hypotenuse. Now, consider angle A. Side BC lies opposite to angle A. Let's call it the side opposite to angle A. Side AB lies next to angle A. It is said to be a side adjacent to angle A. Similarly, let's consider angle C. Side AB is the side opposite to angle C, while side BC is a side adjacent to angle C. Note that the terms opposite and adjacent change based on the angle being considered. The hypotenuse, however, remains the same. Now, let's come back to Jack. We'll move Jack to a position such that a line can be drawn joining the top of the clock tower and Jack's head. Oh, looks like the top of the tree also falls on the same line. Let's drop perpendiculars from this line to the ground, passing through the clock tower, the tree, and Jack. We now have three right triangles: triangle PQC, triangle ABC, and triangle MNC. Angle C is common to all the three triangles. Each triangle has one angle, which is a right angle. It means that two pairs of corresponding angles of the three triangles are equal. Thus, by the angle sum property, the third pair of angles of these three triangles is also equal. This means that the triangles PQC, ABC, and MNC are similar to each other by the AA similarity criterion. Now, what can we say about the corresponding sides of these triangles? Recall that in case of similar triangles, the three pairs of corresponding sides are proportional. This means that the ratios PQ upon PC, AB upon AC, and MN upon MC are equal. Now, let's consider angle C in all the three triangles. In relation with angle C, sides PC, AC, and MC are all hypotenuses, and sides PQ, AB, and MN are all sides opposite to angle C. Thus, we can see that, with respect to angle C, the ratio of the opposite side and the hypotenuse for all the three triangles are constant. This constant ratio can be written as opposite side of angle C divided by hypotenuse. In trigonometry, this ratio is given a name. It is called the sine of angle C. The sine of angle C is written as sine C. Here, angle C is an acute angle. The sine of an acute angle in a right-angled triangle is defined as the ratio of the side opposite to the acute angle and the hypotenuse. Similarly, in relation with angle C, sides PC, AC, and MC are hypotenuses, and sides QC, BC, and NC are sides adjacent to angle C. The ratio of the adjacent sides and the hypotenuse is also constant. This constant ratio is named as the cosine of angle C. The cosine of angle C is written as cos C. The cosine or cos of an acute angle in a right-angled triangle is defined as the ratio of the side adjacent to the acute angle and the hypotenuse. Similarly, for triangles PQC, ABC, and MNC, the ratio of sides opposite to angle C and sides adjacent to angle C is constant. This constant ratio is named as the tangent of angle C. The tangent of angle C is written as tan C. The tangent or tan of an acute angle in a right-angled triangle is defined as the ratio between the side opposite to the acute angle and the side adjacent to the same acute angle. Let's recap the three trigonometric ratios that we just discussed. The table shows the trigonometric ratios for an acute angle of a right triangle. The measure of the acute angle is taken as theta. Now, here's an easy way to remember these trigonometric ratios. Look at the bold letters. They form a mnemonic. So, ka, to. It is pronounced so, ka, to, a. The so stands for sine of an angle is opposite side over hypotenuse. The CA stands for cosine of an angle is adjacent side over hypotenuse. The TOA stands for tangent of an angle is opposite side over adjacent side. Memorize this to remember these ratios. Apart from the three primary trigonometric ratios, the reciprocals of these ratios are also defined. The cosecant or cosec of an acute angle in a right-angled triangle is the reciprocal of the sine of the angle. Thus, the cosecant of angle C or cosec C is equal to the ratio between the hypotenuse and the side opposite to angle C. Or, the cosecant of angle C is equal to AC upon AB. The secant or sec of an acute angle in a right-angled triangle is reciprocal of the cosine of the angle. Thus, the secant of angle C is equal to the ratio between the hypotenuse and the side adjacent to angle C. Or, the secant of angle C is equal to AC upon BC. The cotangent or cot of an acute angle in a right-angled triangle is reciprocal of the tangent of the angle. Thus, the cotangent of angle C is equal to the ratio between the side adjacent to angle C and the side opposite to angle C. Or, the cotangent of C is equal to BC upon AB. Here are all the 6 trigonometric ratios of an acute angle of a right triangle. The values of trigonometric ratios do not vary with the lengths of the sides if the angles remain the same. Thus, we can conclude that trigonometric ratios are only dependent on the ratio of the sides and not on the lengths of the sides. An important point to note is that when the square of these ratios is written as sine square c in place of sine c square, this applies for all trigonometric ratios. Let's try an example. Consider a right triangle ABC. Its two sides are 3 units and 4 units respectively, and its hypotenuse is 5 units. For angle C, the opposite side is AB, which is 3 units, and the adjacent side is BC, which is 4 units. Let's find the trigonometric ratios for angle C. Sine C will be equal to opposite side to angle C divided by hypotenuse, which is equal to 3 divided by 5. Cos C will be equal to adjacent side to angle C divided by hypotenuse, which is equal to 4 divided by 5. Tan C is equal to opposite side to angle C divided by adjacent side to angle C, which is equal to 3 divided by 4. Cosec C is reciprocal of sine C, hence it is equal to 5 divided by 3. Sec C is reciprocal of cos C, hence it is equal to 5 divided by 4. And cot C is reciprocal of tan C, hence it is equal to 4 divided by 3. Now, consider the other acute angle, angle A in the right-angled triangle ABC. Are the trigonometric ratios for angle A same as those of angle C? As you can see in the table, the trigonometric ratios of angles C and A are different since their adjacent and opposite sides are different. In case of the trigonometric ratios of an acute angle in a right-angled triangle, if any one of the ratios is known, all the other trigonometric ratios of the angle can be calculated. We'll apply this understanding to help Jack find the height of the clock tower. In triangle MNC, side MN, which represents Jack's height, is equal to 6 feet and side NC is 8 feet. With reference to angle C, MN is the opposite side and NC is the adjacent side. Thus, tan C is equal to opposite side to angle C divided by adjacent side to angle C, which is equal to 6 divided by 8. On simplifying, we get 3 divided by 4. Now, the distance between point C and the base of the clock tower, which is represented by side QC, is 40 feet. In triangle PQC, side QC is the side adjacent to angle C. Let's assume the height of the tower, which is represented by side PQ, as x. Tan C is equal to PQ divided by QC, which is equal to x divided by 40. We know that tan C is constant. Thus, ratio of PQ and QC is equal to ratio of MN and NC. Substituting the values, we get x upon 40 is equal to 3 upon 4. On simplifying, we get the value of x as 30 feet. Therefore, the height of the clock tower is 30 feet. Let's solve some more examples. Here, one trigonometric ratio is given. We will use this ratio to find the other trigonometric ratios. Consider angle C in the given figure. It is given that cos C is equal to 4 by 5. Now, cos C is equal to the ratio between its adjacent side BC and hypotenuse AC. Thus, we can say that AC is equal to 5x and BC is equal to 4x, where x is some constant. The reason we include a constant x here is that the trigonometric ratio just gives us the proportions of two sides, not their exact values. In both these triangles, cos C is 4 by 5, though the actual lengths of their sides are different. Now, using Pythagoras' theorem, we can find the length AB. Putting in the values and simplifying, we find AB is equal to 3x. Since we know the values of all the three sides of triangle ABC, we can calculate all other trigonometric ratios. For example, sin C is equal to 3x upon 5x, or 3 by 5. Similarly, tan C is equal to 3x upon 4x, or 3 by 4. Let us take another example. Suppose in the given right-angled triangle ABC, sin A is equal to 2 by 3. Now, sin A is equal to the ratio between its opposite side BC and hypotenuse AC. Thus, we can say that AC is equal to 3x and BC is equal to 2x, where x is some constant. Again, using Pythagoras theorem, we can find the length AB. Putting in the values and solving, we find AB is equal to root 5x. Now, since we know the values of all three sides of triangle ABC, we can calculate all other trigonometric ratios. For example, cosine of angle A is equal to root 5x upon 3x, or root 5 by 3. Similarly, tangent of angle A is equal to 2x upon root 5x, or 2 by root 5. This brings us to the end of our discussion on trigonometric ratios. Memorize these ratios by heart and try finding these ratios in different right-angled triangles. Welcome to the lesson on trigonometric ratios of specific angles. At the end of this lesson, you will be able to state the trigonometric ratios of angles of measure 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. You will also be able to state trigonometric ratios of complementary angles. Consider angle C in the right-angled triangle ABC. You already know that angle C has some trigonometric ratios associated with it. We are now going to see some special situations with respect to the values of the angle C. Now, let us see what happens if we decrease angle C till it approaches 0. Observe carefully. As angle C decreases, the length of AB decreases. At the same time, point A approaches point B, so that length AC approaches length BC. When angle C becomes 0, we can say that the length of AB, the side opposite to angle C, also becomes 0. Also, the length of hypotenuse AC becomes equal to the length of BC, the side adjacent to angle C. Let us calculate the trigonometric ratios of angle C in this position. We know that sin C is equal to the ratio between AB, the side opposite to angle C, and AC, the hypotenuse. We have seen that AB becomes 0 when angle C is equal to 0 degrees. 0 divided by any quantity is 0. Thus, we can say that sin 0 is equal to 0. We know that cos C is equal to the ratio between BC, the side adjacent to angle C, and AC, the hypotenuse. We have seen that AC becomes equal to BC when angle C is equal to 0 degrees. Thus we can say that cos 0 is equal to 1. We know that tan theta is equal to sin theta divided by cos theta. Substituting theta equal to 0 degrees and simplifying, we get tan 0 degrees is 0. Let us look at other trigonometric ratios of 0 degrees. Cosec 0 is equal to reciprocal of sin 0, which is 0. Since any quantity divided by 0 is undefined, cosec 0 is undefined. Sec 0 is equal to reciprocal of cos 0. Thus, sec 0 is equal to 1. Cot 0 is equal to reciprocal of tan 0. Therefore, cot 0 is undefined. Let us quickly recap the trigonometric ratios of an angle that measures 0 degrees. Consider angle C in the right-angled triangle ABC. Now, let us see what happens if we move angle C till it approaches angle B, which is equal to 90 degrees. Observe carefully. As angle C increases, the length of BC decreases. At the same time, point C approaches point B, so that the length AC approaches the length AB. When angle C becomes 90 degrees, we can say that the length of BC, the side adjacent to angle C, also becomes 0. Also, the length of the hypotenuse AC becomes equal to the length of AB, the side opposite to angle C. Let us calculate the trigonometric ratios of angle C in this position. We know that sin C is equal to the ratio between AB, the side opposite to angle C, and AC, the hypotenuse. We have seen that AC becomes equal to AB when angle C is equal to 90 degrees. Thus, we can say that sin 90 is equal to 1. We know cos C is equal to the ratio between BC, the side adjacent to angle C, and AC, the hypotenuse. We have seen that BC becomes 0 when angle C is equal to 90 degrees. 0 divided by any quantity is 0. Thus we can say that cos 90 is equal to 0. We know that tan theta is equal to sin theta divided by cos theta. Substituting theta equal to 90 degrees and simplifying, we get tan 90 degrees is undefined. Let us move on to other trigonometric ratios of 90 degrees. Cosec 90 is equal to reciprocal of sin 90, which is 1. Thus, cosec 90 is equal to 1. Sec 90 is equal to reciprocal of cos 90, which is 0. Thus, sec 90 is undefined. Cot 90 is equal to the ratio of cos 90 and sin 90. Hence, cot 90 becomes 0 upon 1, which is equal to 0. Thus, cot 90 is equal to 0. As tan 90 degrees is undefined, we do not consider the definition that cot of an angle is the reciprocal of tan of the angle. Let us quickly recap the trigonometric ratios of a 90-degree angle. Consider a right-angled triangle ABC, in which angle C is equal to 45 degrees. Now, this has some interesting effects on triangle ABC. Given angle C equal to 45 degrees and angle B equal to 90 degrees, by angle sum property, we find that angle A is also equal to 45 degrees. Since sides opposite to equal angles in a triangle are equal, we can say that the length of AB is equal to the length of BC. Let this length be x. Applying Pythagoras' theorem in triangle ABC, we find the length of hypotenuse AC as root 2 times x. Now, we are all set to find trigonometric ratios of the 45-degree angle C. Sin 45 degrees is equal to the ratio of AB, the side opposite to the angle C, and the hypotenuse AC. Putting in the values of AB and AC, we get sin 45 degrees as 1 by root 2. Cos 45 degrees is equal to the ratio of BC, the side adjacent to the angle C, and the hypotenuse AC. Putting in the values of BC and AC, we get cos 45 degrees as 1 by root 2. Now, tan 45 degrees is equal to the ratio between sin 45 degrees and cos 45 degrees. Since sin 45 and cos 45 are both equal to 1 by root 2, tan 45 is equal to 1. Cosec 45 is equal to the reciprocal of sin 45 degrees. Thus, cosec 45 is equal to root 2. Sec 45 degrees is equal to the reciprocal of cos 45 degrees. Thus, sec 45 degrees is equal to root 2. Note that sin 45 degrees is equal to cos 45 degrees and cosec 45 degrees is equal to sec 45 degrees. Cot 45 degrees is equal to the reciprocal of tan 45 degrees. Since tan 45 degrees is equal to 1, cot 45 degrees is also equal to 1. Let us quickly recap the trigonometric ratios of 45-degree angle. Consider an equilateral triangle ABC. By definition, each angle of an equilateral triangle is equal to 60 degrees and all its sides are equal. Let the length of each side of equilateral triangle ABC be x. Let us draw a perpendicular AD from vertex A to its opposite side BC. Again, by definition, a perpendicular drawn from a vertex to its opposite side in an equilateral triangle bisects the angle at the vertex and its opposite side. Thus, AD divides angle A into two equal parts. It also divides side BC into two equal parts, BD and CD, each equal to x by 2. Applying Pythagoras' theorem to triangle ADB, we get the length of side AD as root 3 by 2 times x. Now, let us find trigonometric ratios of angle B equal to 60 degrees in triangle ADB. Sin 60 degrees is equal to the ratio of AD, the side opposite to the angle B, and the hypotenuse AB. Putting in the values of AD and AB, we get sin 60 degrees as root 3 by 2. Cos 60 degrees is equal to the ratio of BD, the side adjacent to the angle B, and the hypotenuse AB. Putting in the values of BD and AB, we get cos 60 degrees as 1 by 2. Tan 60 degrees is equal to the ratio between sin 60 degrees and cos 60 degrees. Putting in the values of sin 60 degrees and cos 60 degrees, we get tan 60 degrees is equal to root 3. Cosec 60 degrees is equal to the reciprocal of sin 60 degrees. Thus, cosec 60 degrees is equal to 2 by root 3. Sec 60 degrees is equal to the reciprocal of cos 60 degrees. Thus, sec 60 degrees is equal to 2. Cot 60 degrees is equal to the reciprocal of tan 60 degrees. Since tan 60 degrees is equal to root 3, cot 60 degrees is equal to 1 by root 3. Let us quickly recap the trigonometric ratios of a 60-degree angle. Remember, when we drew AD perpendicular to BC, we not only divided BC into two equal parts, but we also divided angle BAC into two equal parts. Now, let us find trigonometric ratios of angle BAD equal to 30 degrees in triangle ADB. Sin 30 degrees is equal to the ratio of BD, the side opposite to the angle BAD, and the hypotenuse AB. Putting in the values of BD and AB, we get sin 30 degrees as 1 by 2. Cos 30 degrees is equal to the ratio of AD, the side adjacent to the angle BAD, and the hypotenuse AB. Putting in the values of BD and AB, we get cos 30 degrees as root 3 by 2. Tan 30 degrees is equal to the ratio between sin 30 degrees and cos 30 degrees. Putting in the values of sin 30 degrees and cos 30 degrees, we get tan 30 degrees is equal to 1 by root 3. Cosec 30 degrees is equal to the reciprocal of sin 30 degrees. Thus, cosec 30 degrees is equal to 2. Sec 30 degrees is equal to the reciprocal of cos 30 degrees. Thus, sec 30 degrees is equal to 2 by root 3. Cot 30 degrees is equal to the reciprocal of tan 30 degrees. Since tan 30 degrees is equal to 1 by root 3, cot 30 degrees is equal to root 3. Let us quickly recap the trigonometric ratios of a 30-degree angle. Consider the two acute angles, angle A and angle C, in a right-angled triangle, ABC. By the angle sum property of triangles, we know that the sum of angles A, B and C in the triangle ABC is 180 degrees. Angle B in the given triangle is a right angle. Putting in the value of angle B in the previous equation and simplifying, we see that the sum of angles A and C is equal to 90 degrees. Thus, we can say that angles A and C are complementary angles. What is true for triangle ABC is true for all right-angled triangles. The two angles, besides the right angle in a right-angled triangle, are always acute angles and complementary angles. Now, we can also represent angle C as 90 degrees minus angle A. The table here shows the trigonometric ratios of angle A. The table here shows the trigonometric ratios of complementary angle of angle A, that is, angle C, or 90 degrees minus A. Now, let us compare the values of the trigonometric ratios of the two complementary angles. Comparing the two tables, we see that the value of sin 90 minus A, that is, AB upon AC, is also equal to cos A. Similarly, we see that the value of cos 90 minus A, that is BC upon AC, is also equal to sin A. Similarly, we can find relationships between the other trigonometric ratios of angle A and its complementary angle. The table here summarizes the relationships between trigonometric ratios of complementary angles. Welcome to the lesson on trigonometric identities. At the end of this lesson, you will be able to state 3 basic trigonometric identities. You will also be able to apply these trigonometric identities to solve problems. Here is a triangle ABC. By the angle sum property of triangles, we know that the angle A plus angle B plus angle C is 180 degrees. This equation is true in all triangles. An equation that is true for all values of the quantities that it contains is called an identity. Since the equation angle A plus angle B plus angle C is equal to 180 degrees is true for all triangles, this equation is an identity. Consider the right-angled triangle PQR. By Pythagoras' theorem, we know that in the right-angled triangle PQR, the sum of the square of the sides PQ and QR is equal to the square of the hypotenuse PR. Now, let us derive some trigonometric identities by dividing both sides of equation 1 by the squares of different sides of triangle PQR. Let us start with the hypotenuse PR. Let us divide both sides of equation 1 by PR square. Since the numerator and the denominator are the same, the right-hand side of the equation becomes 1, and we get equation 2. If angle R in triangle PQR is equal to theta, then the ratio PQ upon PR is equal to sin theta, and the ratio QR upon PR is equal to cos theta. Putting the values of these ratios in equation 2, we get an equation sin square theta plus cos square theta is equal to 1. This equation is a trigonometric identity. This trigonometric identity is true for all values of angle theta from 0 degrees to 90 degrees. Now, consider side PQ, the opposite side for angle theta. Let us divide both sides of equation 1 by PQ square to get equation 3. Now, in triangle PQR, the ratio QR upon PQ is equal to cot theta, and the ratio PR upon PQ is equal to cosec theta. Putting the values of these ratios in equation 3, we get an equation 1 plus cot square theta is equal to cosec square theta. This equation is a trigonometric identity. From the trigonometric ratios of specific angles, we know that cot 0 and cosec 0 are not defined. Thus, this identity is true for all values of angle theta greater than 0 degrees and less than or equal to 90 degrees. Now, consider side QR, the adjacent side for angle theta. Let us divide both sides of equation 1 by QR square to get equation 4. Now, in triangle PQR, the ratio PQ upon QR is equal to tan theta, and the ratio PR upon QR is equal to sec theta. Putting the values of these ratios in equation 4, we get an equation 1 plus tan square theta is equal to sec square theta. This equation is a trigonometric identity. From trigonometric ratios of specific angles, we know that tan 90 and sec 90 are not defined. Thus, this identity is true for all values of angle theta greater than or equal to 0 degrees and less than 90 degrees.